Good morning, myself Dr. M. Nagaraj, working as a professor in the Department of Physics. Today I am going to cover the topic of optical fibers. What are optical fibers? Optical fibers are light guides or wave guides. These optical fibers mainly uses for communication for very long distance. Optical fibers are also called as light guide or wave guide. The information from one place to another place transmitted in terms of light. So our information signal is superimposed into the light signal. First, whatever we are going to suppose you take a telephone, okay, when our voice signal is converted into electrical signal, that electrical signal needs to be converted into optical signal. When optical signal it is converted into optical signal, it will transmit it for a long distance through the optical fibers. Here, today's class, I am going to cover how the optical signal is transmitted through the optical fibers. First, we should know the structure of the optical fibers, then propagation mechanism, then principle of operation of optical fibers, and different types of optical fibers. What are the advantages of optical fibers? We are going to discuss in detail about that. First, let us know the structure of optical fibers. Here, optical fibers are made up of glass or plastics. Glass or plastics. Glass means especially we are going to use silica materials. To fabricate these optical fibers, we are going to use glass or plastics. In the structure of optical fibers, mainly it is having core with the refractive index of N1, and it is having cladding with the refractive index of N2. Always the refractive index of the core is greater than refractive index of the cladding, that is N1 is greater than N2. Why we need refractive index of the core greater than refractive index of the cladding? It is because the light should be confined within the core. Later on I will discuss about that. So light will be confined within the core, that transmitted for a long distance. Okay, both core and cladding are made up of same materials, but only the difference is refractive index. Here refractive index of the core is greater than refractive index of the cladding. Here initially the core will be there, on the surface of that the cladding is fabricated. On the surface of the cladding a supporting material is coated, that is called as polyurethane jacket. It will provide the support to avoid the environmental conditions. So this is about the structure of optical fibers. What is the principle of operation of optical fibers? That is called as total internal reflection. That is called as total internal reflection. This is the basic principle of operation of optical fibers. Here from this diagram we can explain what is total internal reflection. Suppose you consider two mediums with the refractive index of N1. This is refractive index of the two medium. This is the x and x dash is the separation between the two mediums. Separation between the two mediums, and this is called as normal. This is called as normal. This line, vertical line, this is called as normal. This is the intersection between the two medium, that is with the refractive index of N1 and refractive index of N2. Okay, suppose I consider a ray A which falls on the which falls here between A and O. It will refracted to the another medium. It has been refracted to the another medium. This incident angle is called as θ1, and refracted angle it is called as θ2. Now, you further increase the incident angle. That is called as incident angle. Now it is called as θc. Now, when this ray is incident with the incident angle θc, it will grazes the interface between the core and cladding. It will grazes here. It will transmits in the intersection of both the medium, that is refractive index of the N1 and N2. That is called as critical angle. Now you further increase the incident ray angle, what happens? Completely it will reflected back towards the same medium. This is called as COC dash. So here from this diagram we can say that whatever the rays which falls above the critical angle, those rays are undergoes total internal reflection. Total internal reflection means the rays which falls in the same, which falls and it will reflect it back towards the same medium. Those rays are called as internally reflected rays. Here this diagram, whatever the rays which falls above the critical angle, those rays undergoes what? Totally internally reflected. That's why it is called as totally internally reflected rays. Finally, what we can conclude that the rays which should fall above the critical angle in order to confine the light within the core material. Here, importance of TIR. Importance of TIR. Here, suppose you consider one optical fiber. It is called as cladding. It is called as cladding with refractive index of N2. This is core with refractive index of N1. A ray is falling here at the interface of core and the cladding. Here what happens? Total internal reflection will take place. And it will reflect it back towards the opposite side. Means it is reflected back towards the same medium. When it will incident on the core and cladding interfaces here is also TIR will takes place. And once again it will reflect it back towards the opposite wall of the optical fiber. Here is also total internal reflection will take place. Suppose you consider if any one point, if there is no internal reflection takes place, what happens? It will radiate outside from the optical fiber. It will radiate outside from the optical fiber. Means the light rays will enter into the cladding material and outside the optical fiber. That is the importance of optical fibers. For every when a rays is interface, when it will bombard in the interface of both core and cladding, every interface it should total internal reflection should takes place. If there is no TIR, the light will radiate outside from the optical fiber. Therefore, the loss of signal will takes place. And there is one formula is there. For example, for same here we can derive what is the theta c. We can derive that. How we can derive? For example, using Snell's law, we can derive it. Using Snell's law. We have to apply the Snell's law for ray AO A dash. N1 sine theta 1 equals to N2 sine theta 2 for AO. Now we apply the Snell's law for this BO B dash. Here what happens? N1 sine, what is incident angle here? Theta c we have to take it, and N2 sine of, what is the angle here? Sine of the refracted angle is 90 degree. Refracted angle is 90 degree. Here N1 sine theta c equals to N2 because sine 90 equals to 1. Sine 90 equals to 1. Therefore, we can write it as theta c equals to sine inverse of N2 by N1. If you know the value of refractive index of both core and cladding, we can derive the expression for critical angle, that is theta c equals to N2 by N1. And we have different types of optical fibers. Mainly step index fibers, another one is graded index fibers. In step index fibers, once again two types, step index single mode fiber and step index multi-mode fiber. This diagram provides step index single mode fiber. In step, why it is called as step index? Here there is a step difference between the refractive index of the core and cladding. There is a step difference. This is refractive index of cladding, this is refractive index of N1. There is a step difference between the refractive index of the core and cladding. That's why it is called as step index. It supports only one mode of propagation. It will supports only one mode of propagation. That is called as single mode optical fiber. And why it supports only single mode? It is because the diameter of the core is very less. The diameter of the core is around 8 to 10 micrometer only. Because small core radius, it supports only single mode, and cladding diameter is around 100 to 150. The cladding diameter is around 100 to 150 micrometer. Because of very small core diameter, it supports only single mode. So one of the main advantages of this single mode optical fiber is it supports very large bandwidth. It supports large bandwidth. That is the main advantage of this optical fibers. The main optical source will be used for this single mode optical fiber is lasers. We have to use lasers. So one of the main limitation of this single mode optical fiber is the splicing is difficult. The disadvantage of this single mode fiber is splicing is difficult. Splicing is difficult. Why splice? What is splicing? Splicing means it is a joining of two optical fibers. Very skillful persons are required to join the two optical fibers because the core diameter is very small, around 8 to 10 micrometer. If there is any small misalignment takes place, is there any gap between the two optical fibers or misalignment will takes place, what happens? The loss of signal will takes place. That's why the splicing is little bit of difficult. And next we have step index multi-mode fiber. Step index multi-mode fiber means it is also there is a step difference between core and cladding is there. But the difference between step index single mode and step index multi-mode is core diameter is very large. And cladding diameter, as it is around 100 to 250, it is having 50 to 100 micrometer. This is cladding diameter is around 100 to 250 micrometer it is having. That's why because of large core diameter, it supports more than one modes. That's why it is called as step index multi-mode fiber. So one of the main disadvantage of this step index multi-mode fiber is it is having group velocity dispersions. GVD we call it as group velocity dispersion. Group velocity dispersion means, as I said, it supports more than one modes. Means it is, that's why it is called as multi-mode fiber. All the modes are excited at the same time at the source, but at the destination, at the receiving side, different modes will reach at different time. That's why it is that phenomenon is called as group velocity dispersion. And we can use the light source for this step index multi-mode fibers. We can use either both laser and LEDs can be used. And last type of optical fiber is called as graded index optical fiber. Graded, why it is called as graded index fiber? Here refractive index of the core is graded. Refractive index of the core is graded here. How it is graded? It will be in the what? It will be the parabolic form or triangular form. Here you can observe here refractive with the variation of the refractive index of the core, it is varied here, and means it is graded. So as we go away from the center of the core to the interface of the core and cladding, as we move away from the center of the fiber axis to the interface between the core and cladding, the refractive index goes on decreases, and at the interface of both core and cladding, the refractive index of the core becomes equal to the refractive index of the cladding. That's why it is called as graded index fiber. And not only parabolic, we can use even a triangular form also. This is called as refractive index profile. Refractive index profiles we call it as, and it supports by default it is called as multi-mode. It supports more than one mode. That's why it is called as multi-mode. The core diameter as well as cladding diameter is same as multi-mode fiber only. Core diameter is around 50 to 100 micrometer, and cladding diameter is 100 to 250 micrometer. The another important concept I am going to introduce now, that is called as numerical aperture of the optical fiber. Numerical aperture. Numerical aperture of an optical fiber. Numerical aperture of the optical fiber means it is called as the light gathering capability of the optical fiber. Light gathering capability of the optical fiber means if we join two fibers, here, I will take two fibers here. This is cladding. This is also cladding. This is core of one fiber. This is also core of another fiber. This is called as cladding. This is also core. When two fibers are joined, when optical signal is transmitting from fiber 1 to fiber 2, okay, already we know light will be propagated in the optical fiber. Light means it is a group of photons. Light means group of photons. When 100 photons are coming from fiber 1, it should enter into the fiber 2. Same 100 photons should coupled from one fiber to the another fiber. Here what happens, sometimes during coupling of 100 photons from first fiber to the second fiber, there is some loss will takes place. If it is 100 photons are coupled into the second fiber, it is called as numerical aperture is equals to 1. Always the numerical aperture value is always it is less than 1. If it is numerical aperture Na equals to 0.4, 0.4 numerical aperture equals to 0.4 means if 100 photons are coming from the fiber 1, if 40 photons are successfully transmitted from fiber 1 to fiber 2, that is called as what is the percentage of propagation from photons from one fiber to another fiber? It is called as 0.4, or in terms of percentage we can tell that 40%. If 60 photons are entered from fiber 1 to fiber 2, 60 photons, it is called as numerical aperture, we call it as 0.6, means 60% what we call it as. And numerical aperture of the optical fiber we can calculate it using refractive index of the both core and cladding, that is Na equals to square root of n1 square minus n2 square. We can derive this equation. There is using Snell's law we can derive this numerical aperture. Next, I will come across the attenuation in optical fibers. What is attenuation? It is a loss of signal as it propagates along the optical fiber. Suppose you consider one optical fiber having 100 km length. Suppose you consider around 100 watt optical fiber is inputted here. At the receiving end, we may observe around 80 watt. At the input side, we have inputted at 100 watt, but the output side means this is transmitter, this is receiver. At the transmitter side, we have inputted the optical fiber with the 100 watt, but the output side means at the receiving side, we have 80 watt. Means how much loss has been taken place? Around 20 watt loss has been taken place. This is called as attenuation, the loss of signal as it propagates along the optical fiber. That is called as attenuation. That attenuation can be calculated using called as attenuation coefficient. Attenuation coefficient, that is called as alpha. Alpha equals to minus 10 divided by L log base 10 P out by P in, that is decibels per kilometer. You can calculate the attenuation of the optical signal with respect to length, input power as well as output power. For this, what is the reason behind the loss of signal? There are many reasons are there. First one is absorption of light. Due to absorption of light. Second one is due to scattering. Last one is radiation loss. Radiation loss. These are the three reasons behind the loss of signal, means attenuation of the signal as it propagates along the optical fiber. In absorption, once again, it is having two types: intrinsic absorption, and second one is extrinsic absorption. What is first we should know what is absorption. Absorption means when light signal is propagating along the optical fiber, the absorption of the photons will take place. That is called as absorption of light. There are two types of absorption. One is intrinsic absorption, another one is extrinsic absorption. Intrinsic absorption means, already we know that optical fibers are made up of glass or plastics. When light signal is propagating along the optical fiber, the material which are fabricated the optical fibers, that material itself absorbs the incoming light. That is called as intrinsic absorption. The material itself, either silica or plastic, that material itself absorbs the light. That is called as intrinsic absorption. The extrinsic absorption means, suppose you consider to fabricate optical fibers, if you use silica. Okay, actually pure silica material should be there, but it will not be pure. Some impurities are also present. That impurities are also called as some foreign materials. Okay, so that due to presence of impurities, the extrinsic absorption will take place. So these impurities are also called as some transition metals. Those are also called as some transition metals. When these transition metals absorbs the light, those metals will go to ground state to excited state. It will stay there for a period of time. They will come back to the lower energy state by emitting a photons. Those photons are called as unwanted one. So this is called as absorption. Next one is called as scattering. Scattering means, suppose you consider an optical fiber here. If there is any density variations takes place during fabrication of the optical fibers. Always the core should be uniform, the density of the materials should be uniform throughout the optical fibers. In the cladding also, the distribution of the particles or density of the particles should be constant throughout the optical fibers. In the core also, density of the particles should be constant throughout the optical fibers. But during fabrication, it will not happen. There is density variations will take place. Small density variations will take place. When an incoming photon will comes here, what happens? It will interact with the density variations. After interaction with the density variations, the photon of light will be radiated outside from the optical fiber. This is called as scattering. Scattering means interaction of the photon or scattering of the photon by the density variations. The photons will radiate outside from the optical fiber. That is called as scattering loss. That is called as scattering loss. The last one is radiation loss. And radiation loss, once again we have two types. Micro bending and macro bending. Radiation loss. It is also called as bending loss. It is also called as bending loss. Once again, it is having two types: micro bending. Second one is macro bending. Micro bending, macro bending. Macro bending means, suppose you consider an optical fiber like this. Here how it looks? It looks like a bending, curved shape optical fiber. Curved shape optical fiber here. You take two ends of the optical fiber, just to bend it. That bending is called as macro bending. As if you hold the two ends of the optical fibers, just to drag it, what happens? Still bending will take place. Here what happens? Radius of curvature, it is called as radius of curvature. As we bend the optical fiber, radius of curvature goes on, decreases. Whatever the signal propagates here, wherever bent places are there, there is no TIR will take place. It will radiate outside from the optical fiber. Wherever the bent places are there, on that place, no total internal reflection will take place. Therefore, the light will radiate outside from the optical fiber. As we bend more and more, the radius of curvature goes on, decreases. As radius of curvature decreases, the loss of signal will also be more. So another one is called as macro bending. Macro bending means a small fluctuations on the surface of the optical fibers. On the surface of the optical fibers, a small fluctuations you can observe here. Here when light is propagating, when it undergoes wherever the small variations are there, here in this place, there is no TIR will take place. No TIR will take place. The light will radiate outside from the optical fibers. So this small variations in the surface of the optical fiber is called as micro bending. We can avoid micro bending by placing a weight. Okay. So just as I summarize the things, first we came to know what are optical fibers, the structure of the optical fibers, and basic principle of operation of optical fibers. Type is attenuation, different types of attenuation mechanisms. So these optical fiber, there are various advantages of optical fibers over copper cables are there. First one is, very first advantage of the optical fiber, for it will be used for very long distance communication. And second one is, there is attenuation will be very less, loss of signal will be very less, and it supports very large bandwidth. Today if you are using internet, It is because of optical fibers only. If there is no optical fibers, there is no broadband data. We cannot name the broadband also. If you are using broadband means we are very large data we are sending from one place to another place. The large data is we are downloading. It is because of optical fibers. Thank you.